All right, good morning. Welcome to Mars. So my name is Michael Geronimo. I'm a senior software developer at Open Robotics. We're the company that does the robot operating system, ROS, and also Gazebo, the simulation environment for robotics. So today I'd like to talk to you about open space. And it's not the kind of open space where you might take your dog for a walk or something like that. It's using open source software for space exploration. But before I dig into the details, I wanted to go through a little history of space robotics. When you think about space exploration, this might be the image that you have in mind, an astronaut on a lunar surface. Or maybe you thought about an astronaut spacewalking out by space station with the Earth far below in the distance. This particular image is of the NASA astronaut Alan Shepard. It was taken by his crewmate Edgar Mitchell during the Apollo 14 mission. That was in February of 1971. 3 months before Apollo 14, in November of 1970, the picture along the bottom was sent back to the Earth. It's a panoramic image taken from the Lunokhod 1. The Lunokhod 1 is the rover in the upper right. It kind of looks like something from an old science fiction movie, but actually it was the first rover to operate beyond the Earth. The Soviet Union created Lunokhod 1, and they followed with Lunokhod 2 in January of 1973, about 50 years ago. The Lunokhods were controlled in real time from the Earth. There was a camera on the Lunokhod, and it relayed images back to the Earth about once every 7 to 20 seconds. And there was a team of 5 people on the Earth that received the images and teleoperated the rover. However, robots like these weren't very well known at the time, and it's probably because they didn't make the same emotional connection with the people back home as the human missions did. But they explored more of the moon, and they did it for longer. For example, the Lunokhod 2 covered 39 kilometers. And the longest trip by any of the human-operated moon buggies at the time was 36 kilometers. Lunokhod 1 also operated for 321 Earth days. But the longest surface EVA time for astronauts was only 22 hours during Apollo 17. In the 50 years since Lunokhod, robots have become increasingly common in space exploration. So rovers have been traveling around the moon and Mars. And in the case of Mars, they've even flown. So NASA's Ingenuity is in the upper right there. It's a small robotic helicopter that has operated on Mars along with the Perseverance rover since they both landed in February of 2021. The Ingenuity flights have proven its ability to fly in the extremely thin atmosphere of Mars. It's over 100 million miles from the Earth. And this is all without direct human control. Radio signals take about 5 to 20 minutes to travel between the Earth and Mars, and Ingenuity operates autonomously. It performs maneuvers that are planned and scripted and sent to it by the folks at JPL. In the bottom middle picture, you can see the Perseverance rover. It's a selfie that the Perseverance took. You can also see a couple holes drilled in the rock there. There was a robotic arm where it was taking core samples. So robots can't do everything that people can, not by a long shot, but they're an essential part of space exploration, and they're becoming increasingly common. And it's not just a mobile robots. This is a Canadarm manipulator. And this manipulator has played a vital role in the space shuttle program, and it's still used in the space station today. The original Canadarm was used to deploy payloads up to 65,000 pounds in space. In the mid-90s, the arm was redesigned, and it increased the payload capacity to 586,000 pounds, and it supported space station assembly operations. The Canadarm can also be used to retrieve and repair and deploy satellites. So there are many kinds of robotic space systems in use today, as well as planned. We've seen like the manipulators, like the Canadarm. There are also humanoid robots, like Robonaut 2 on the bottom and Robonaut 5. And they have actually They're very dexterous. They have arms, obviously, and little fingers that can perform very specific tasks. There's mobility systems. On the top is the Viper rover, and there's also the Athlete rover. And there's robotic spacecraft and robotic landers as well. So in the future, we're going to see all kinds of robots used for various tasks, such as mining, excavation, maintenance and repair of systems, manufacturing in space, preparing sites, and lots more. But with all of these applications and robots comes a corresponding increase in the overall complexity of the systems, especially the associated software. The amount of software in these systems is increasing at a very steep rate. So imagine the Lunokhod rover of 1970. Now, I don't know how many lines of code were on the Lunokhod rover, to do the teleoperation of the rover, but definitely minuscule compared to the 2 million plus lines of code on the Perseverance rover in 2020. So writing custom software for each mission might have been a viable thing to do in the past, but no more. That's because writing custom software for each mission can result in high development costs, minimal reuse of the code, and can be time-consuming to qualify that software for use in space. The result is that there's an increasing demand for reuse in space systems in the software. And in fact, the space community is already moving towards componentized, reusable, and open frameworks for flight software missions and mission control systems. So there's a couple flight systems. One's F prime, another is CFS, the core flight system. These are both open source, and they're from NASA. And there's a couple mission control systems. One's called YAMS, another's OpenMCT. And some missions are also using smaller open source projects. One example is AprilTag. So it's a visual fiducial system. There are markers that can be put on a robot, and these identify locations. They can also be used to be associated with information, kind of like a QR code that you can scan. So the trend towards using open source software is, in general, for space systems, is very clear. We need to achieve the reuse and of using these systems for subsequent missions. So to dig in a little bit on F prime, to see the types of attributes that we're looking at that are important for reuse, I've tried to highlight here. So F prime is a software framework for rapid development and deployment of embedded systems in spaceflight applications. It was written originally at NASA's JPL. F prime is open source, as I mentioned. It's already been deployed on several missions. It's a C++ framework, and it abstracts the operating system. And it has a component architecture with well-defined software interfaces. And there's a standard library that comes with F prime of flight-worthy components that have been used in flight. So you can either use the standard components or write your own components to plug into this architecture. It also supplies tools for automatically generating code from system designs. So model-based design tends to be important in this segment, as well as testing tools for unit and system level testing. And F prime is typically used for smaller systems like satellites. So there are CubeSats, which are a class of nanosatellite, and there are small sats, which are about the size of a large refrigerator. There's also CFS, and CFS is probably the most popular or common flight software framework. It also provides a dynamic runtime environment with a layered component-based design. But you can see that these are attributes that the industry is demanding. And the reason is, as you can see in the quote from NASA, the reuse drives a significant cost savings, as well as time. So meanwhile, back here on Earth, in the broader robotics community, has standardized on ROS. That's from Open Robotics. So ROS is an open source platform for building robotics applications. It includes communications middleware, drivers that interface to hardware, state-of-the-art algorithms, and a wide range of developer tools. So implementing a robot for space applications like those we've seen can be greatly simplified by incorporating a robotics framework along with the flight system. So, for example, like ROS has a whole ecosystem of packages. There's a package like Move It 2 that can plan and execute motion for manipulators, like the Canadarm, for example, or those hands and fingers that we saw on the Robonauts. There's another package called Navigation 2 that can provide the means for robots to plan and execute paths and avoid obstacles and travel from point A to point B. ROS started around 2007 as a project of a couple PhD students at Stanford University in their robotics lab. Their motivation was to help people spend more time actually building robots rather than working on the infrastructure required, all that software infrastructure that's necessary. So ROS is really the open source platform that's driving the global robotics industry. But an important point is ROS is more than just the source code base. Whoops. There, that's it. So ROS has a thriving ecosystem of developers around the world that contribute to ROS. For example, the most recent release of ROS is called Humble Hawksbill. It had contributions from 198 different sources in academia, government, and industry. So ROS is also commonly used at the university level and sometimes even down to high school robotics teams. So this is a great benefit, so that roboticists come out of the education pipeline with ROS experience already. At university, they might work on ROS-related research projects and robots. They become familiar with the APIs, the tooling, and the packages provided by ROS and its ecosystem. And the ROS ecosystem is continually growing. You can see here, I've cited several statistics about the number of research articles that cite ROS is up, the number of unique visitors that are downloading and using ROS for their robotics projects. And there's also a couple websites that you can go to for asking and answering questions and discussing ROS topics. So it has a very lively growing ecosystem. The latest version of ROS is ROS 2. So ROS 2 offers a standard software platform that was built from the ground up for use in high reliability and safety critical systems. Previously, with ROS 1, prototype code, it was very popular to write quick prototype code, put them together, and create systems. And often this would have to be rewritten for production. ROS 2 is meant to address that you can carry through the code that you've written for prototyping or research and bring that through without having to rewrite it for an entirely different system. Another advantage is there are many working groups that work on ROS on different topics. And this is not just from Open Robotics, but out in the community. And they help to advance it in a lot of different ways. And a couple that are relevant to space exploration are the safety and real-time working groups. ROS 2 is also multi-platform. It runs on Linux, Windows, and Mac OS, and it uses an industry standard DDS implementation as its core middleware. DDS is a data distribution system. It's a very industrial strength communications middleware that ROS 2 is built on. So you can actually choose to use a different DDS provider, or you can actually, it doesn't actually have to be DDS. There's an abstraction that we'll see later. You can actually plug in your own middleware if you have something that you'd like to use instead that has to interface to the bottom layer. So DDS is used for high reliability systems like air traffic control, autonomous vehicles, medical devices, and power grid management, things that are very safety critical, high reliability, high availability kinds of systems. So ROS robots are everywhere on Earth. So you'll find ROS inside toys and drones, delivery robots that like you might find on a college campus, agriculture, underwater robots, it's everywhere. And it's safe to say that if there's a commercial robot, it's probably based on ROS, or at least has some ROS code in it. And given its open architecture, companies are able to compose systems combining existing packages. That's where they can leverage the work of others in the community, and because of the kind of component-based architecture, bring these together and compose a system and add their specific code to the whole system to achieve the robot application that they desire. Excuse me. And you might be surprised to know that ROS has already actually been to space. It was used for Robonaut 2 in 2014, and it's also used on the Astrobee robot in 2019. So NASA created this free-flying robotic system, that cube there, that was intended to help robots and kind of offload some of their routine duties, to leave them more time to focus on other things that only people can do. So the Astrobee system consists of 3 cube-shaped robots, and along with software and a docking station for recharging. The robots actually use an electric fan to propel them throughout the space station. And they have a camera and sensors so that they can see and navigate their surroundings. They can work autonomously or via remote control and do a lot of tasks for the astronauts, such as taking inventory, documenting experiments, and they can even work together to move cargo throughout the space station. And there are currently 3 Astrobee robots on the ISS, and they've been operating since 2019. And the team that that developed the Astrobee released their ROS-based code on GitHub, including Gazebo software simulation. So this helps, they're able to share it with others in the community, so you can take that code, learn from it, expand on it. The Astrobee package consists of flight software that runs on the Astrobee robot, a software simulator, and tools that are written in C++. And I have a little video just to take a quick break and show you a little bit more about the Astrobees and the science carried out on the space station.
Greetings from the White House, which is where I am right now. Congratulations on all of your success and just being women in space.
Hey, Madam Vice President, I can't believe we just got to say that from the International Space Station.
You all are such incredible role models. Tell us a little bit about what work you are doing up there. What are you researching?
We have so much research going on up here. It is absolutely amazing. Just about every field you can imagine. This week I was working with some free-floating satellites inside. Actually,
whoa!
We have one right here. And so we're using this technology to test out new things that'll help us on future exploration missions, namely to the Moon and Mars. What we're hoping is to get these robots to be able to maintain our vehicles when we're not around. We've got over 100,000 nematodes, little tiny worms. We're going to be studying those worms to look at how muscle strength changes when you're in space.
What is your advice to our young girls and boys out there who maybe could never imagine themselves being astronauts, being scientists? Tell them about the joy that you have in doing what you do.
I don't think any of us ever really thought we would be astronauts. I think this is pretty true of everybody in our office. So I would encourage everybody who's even thinking about it, just don't hold yourself back. I think everybody here, all of our crew members, do what we do because we love it. We love every minute of it. And science can be like that. Science is hard work, and people get scared by the coursework, and they think it's rigorous and it's going to be too hard for them. Science is amazing. It is so much fun. It makes every day fun, and we love it. And we love doing science in space.
I want you guys to know how grateful we are. Come see us at the White House when your feet are back on the ground. And again, just take care and thank you.
So we're excited about that, ROS already being in space. And there are other projects that are in the works. There's NASA's Viper mission, and it will make pretty extensive use of ROS as well. So Viper is a mission to the moon, and it will go to the lunar south pole of the moon, prospecting for resources, in particular for water. And ROS is used in the loop on the ground, so ground software systems. for that. So there's some images that come down, there's some image stitching, there's some terrain registration, and there's some localization that all happens on the ground data systems, and that is using ROS. Also making extensive use of Gazebo, the simulator I mentioned. So this helps the team to, with the simulation of the lunar surface and the Gazebo simulator, they're able to navigate the rover, the simulation of the rover through this environment, and do lots of testing with the Viper rover. And in fact, we're dialing in the testing and comparing it to a physical lab that they have. There's something called a slope lab, and they have models of the rover, actually physical rovers, and they're able to adjust kind of slopes and make craters and test the rover in this environment and then compare it with the simulation so that we can make the simulation more accurate. And there's a lot of time spent on lighting and to get this all right. And so this enables you to run lots of extensive tests. There's an end-to-end testing system that's running, it's testing all of the different subsystems on the Viper rover. So simulation helps a great deal here. So we're excited that ROS is used here and the Gazebo simulator is used. They're also using other open source software for this project. There's a bridge from ROS to CFS, the core flight system that I mentioned earlier, that was used. And there's the mission control software, YAMS and OpenMCT, and there's another one called Verb that's also used. So a very, not complicated, but extensive system of the flight software, the ground software, mission control, and all of this. So to be on the flight side of things, NASA requires the software to be space qualified, which is why ROS is not on the flight system. It's used on the ground, or it's used for the Astra-B. There were certain guarantees they would have to make about safety. That's how it was able to get on the Astra-B free floating, that it wouldn't harm anybody and that they could guarantee that it would be safe in that use. So this is important, the space qualification, according to aerospace standards. So what we really need is a version of ROS for space applications, and that's really the key of what I want to emphasize here, is that how do we get ROS to be used on the flight side, and what's needed to bring ROS really into space. So what we need is a space certifiable and reusable robotics framework, right? We've seen there's all these packages, there's a ROS ecosystem. How can we bring this advantage? There's all this demand for reuse from the aerospace industry, and we've got this ROS robotics system and ecosystem. We want to bring these together. So it's designed to meet flight software standards and aligned with NASA. NASA has their own standards in this regard, and they have something called Class A missions. They have different levels of classification. So this will enable rapid development of new robotics capabilities, like we've talked about. You can bring off-the-shelf packages together and have it based on open community. This would not be a closed source effort. It would continue like ROS to be open source, have it open frameworks, open standards. So we want to support certification. The aerospace standard DO-178C and the NASA standard is NPR 7150. And what we're aiming to do with Space ROS is to provide the artifacts into that process, that align with that process, so a program or project can take the software through the certification process. And so a big emphasis on this is on code quality, as you can imagine. So there's a lot of emphasis on software and code analysis tools to assess the state of the code and improve the code and feed back that information. So we want static analysis, testing, dispositioning and addressing issues, requirements traceability, all the way from requirements down through to the packages in the code. And of course, there's certain features that have to be addressed and added to the core of ROS to make it suitable for this type of system. In addition to the core ROS, which we don't necessarily have the space-specific modules, but we'll be adding modules that are relevant for space, such as a star tracker that helps you to do localization, terrain, hazard analysis, things like that that could be reusable for space missions. And support common telemetry and command formats. So there are space standards for how you can command something like a rover and receive telemetry back from the rover, and then view that telemetry in a mission control system. So there's a lot of existing software that we want to interface with. And so this certifying software like this is obviously a really large task, but it's been done before. So this is not a new idea. So ROS has been certified for the automotive industry. So the company Apex AI has achieved ISO 26262 certification, which is kind of the automotive version of the aerospace standards. Each industry has its own standards by which you have to conform to achieve kind of that level of safety certification. And Apex OS was actually certified up to ASIL D, which is the highest level in ISO 26262. And they're able then to use Apex OS for safety critical mobility applications like automated cars, autonomous cars rather, robotaxis, autonomous tractors, all of these types of applications. So the idea for Space ROS actually started with Blue Origin and NASA. So I wanted to call them out and thank them for starting Space ROS. They called on Open Robotics to help with this since it was based on the ROS code, and we're the experts on the ROS software and related tools. So we're working with Blue Origin and NASA and the different NASA space centers on the Space ROS project. In November of last year, NASA sent out a request for information to the community. So they had this idea, and they want to understand, where the community is at and what do they think of this idea. So they received responses from about 30 different companies, universities, and individuals in the community across different types of organizations and many different companies. Many different countries. The information was intended to validate the Space ROS concept and steer the requirements as we kind of work on the Space ROS roadmap together. Some key takeaways from the RFI is that there was indeed significant interest. So the idea definitely resonates with the community, and they want something like this to support space robotics. Operating in resource-constrained environments is critical. Obviously, you're on embedded platforms, something like VxWorks or RTEMS for an operating system. Security of the overall system is also an important concern for those organizations working on DoD-related projects. And as always, documentation and examples are key. So sometimes there might be companies that maybe make manipulator hardware, for example, and they're not necessarily ROS experts, or maybe they've worked with the first version of ROS. So it's really important to have examples, lots of documentation, and ROS has a pretty good set of documentation, so we want to carry that through to Space ROS and provide lots of examples and docs for the folks, how-to guides and troubleshooting. And a really positive sign was they were interested in contributing. So this is important. We're trying to build a community here, and it's important, and it's nothing that Open Robotics can do on its own or NASA can do on its own. We really need the contributions from the entire community to pull this off. So to drill down a little bit, how many people are software developers? What are we talking to? Okay, great. Got plenty. So there's the layers of the ROS stack, if you're not familiar with it. As I mentioned before, kind of based on, at the core, there's a middleware provider, and that's abstracted by a so-called RMW interface. It's a ROS middleware interface. And so being an abstraction, you can then plug in different providers. It's pretty heavily influenced, that layer, by DDS, and so it's kind of designed that DDS can plug in, but it doesn't have to be DDS. There are implementations of the middleware that are non-DDS implementations. And up above that, you have a ROS client library, or RCL. This is the C-based API, provided that then you can then kind of wrap with the different interfaces, whether it's C++, the RCL CPP, or Python or Java, so you can program ROS and then Space ROS through these interfaces. For Space ROS, we're not going to, it's not necessary to do the Python or Java interfaces. All the code is in C and C++, and that's typical for that type of system. So that's generally kind of the layers of the ROS stack. I won't go into too much detail on that, but the idea is that's the foundation on top of which many packages can be built. And a package is ROS is really kind of a collection of packages. There's the core, and the whole federation of packages that come together. And we expect, as I mentioned, space-specific packages to be pulled together and to be made available to the space community. And this will be on top of, currently we're not yet supporting RTEMS and VxWorks and the embedded systems. That's something on our roadmap to support. I think we'll start with RTEMS being the open source embedded OS. And our initial focus, we've been working on this project for about a year, and the initial focus has really been on static analysis so far and code conformance to the analysis tools. We've established a GitHub organization for the code. We've identified a core set of ROS packages, like what's in the core of Space ROS, and established a continuous integration system for the Space ROS builds. We've also put together Docker scripts so that you can automatically build Space ROS and try it out. And on top of that core, also built MoveIt2, which is a very large library to do manipulation. So using MoveIt2, you can do planning for manipulators and paths and so on. So we've built MoveIt2 as well. So there's also a Docker script for that. The interesting part is we've included additional analysis tools. NASA and Blue Origin, there was a couple tools that they were looking for. NASA's Cobra and one called ICOS. Cobra is a tool that works by parsing the code into tokens. If you're familiar with compilers, it's kind of token-based. And then you write rules against that token stream. So it works for very large code bases. It actually has a mode that you can do interactive queries as well. One thing they talk about is they ingest the whole Linux kernel, and they can do queries of different kinds and assertions against the code. Another is ICOS, which is which runs on executables. It's actually more of a dynamic analysis as well, but it's a very deep analysis. So we're kind of throwing different kinds of tools at the code base. As well, we're looking at AutoZAR C++14 coding guidelines. And so we've recently added support for AutoZAR C++14 analysis to Cobra. And with all these tools, so ROS already had several static analysis tools. So we've gone through all of the analysis tools and output Serif. So Serif is a static analysis results interchange format. So it's a standard format, a JSON-based format for the output of static analysis tools. So all of our tools now, including Cobra and ICOS, now output that. Not necessarily directly. Sometimes we take the output and then we parse their current output and then we generate Serif from that. But the result after a build is we can generate the code, we can analyze the code, we have many static analyzers, and it's all in a common format, standard format. And we have several projects that are underway that we're working on. I mentioned kind of working on the core as well. For example, it's very important to avoid dynamic memory allocation in a system like that because it's a source of non-determinism, and it's something that really becomes not certifiable if you can't make certain guarantees on the code. So we've gone through the requirements and design process, and we're working on the implementation for ROS, which is a fairly big project. There's also an eventing and logging subsystem. For example, some organizations may not want to throw exceptions, kind of a non-local, again, they want it very predictable, so instead they might generate an event, and there might be a monitor program that decides what to do. So rather than throwing an exception, having it caught somewhere else, they would rather generate the event and have this monitor maybe restart the system or restart a subsystem. So these are some important changes that we have to bring into Space ROS that aren't currently in ROS itself. And I mentioned the Serif output. So another important thing is eventually we want to, what we're trying to do is supply artifacts into the certification process. And so Serif plays into this because we want to save the Serif output over time. And so we can track that. How are we doing with a burn down rate? Where are the issues in the code? Did we disposition the issues and say, well, this is not really an issue, so we mark this. And so we want to manage the the issues that are found in the code, and Seraph will help us to do that. And so I mentioned the software quality and compliance activities. So this is kind of a detailed chart, but the idea is that there's automated builds, and there's the coding rules that we're analyzing using the tools, and kind of feeding that back. We've got automated testing, generating reports, and so we're kind of feeding into the acceptance testing. So I think I've kind of buzzed through this a little quickly, but so what we're really trying to do is kind of build this community. As I mentioned, that's the fundamental takeaway, is that it's initiated by Blue Origin and NASA. We're contributing, but what I'm trying to do now is get the message out. I'm talking to companies in the industry, understanding their requirements so that we can prioritize features. And this will be a multi-year effort. You can go out and you can see, though, that NASA, you can look at 10, 20-year plans, and there's a lot in the works. And this is a long-term project that will help benefit space exploration for the long term. And so we have to be in it for the long term, and we need help. We need to build a community around this. So I'm at Open Robotics. If anybody's interested in learning more, feel free to contact me, because I'm in that mode of kind of gathering requirements, talking to companies. And if you're technical and you're curious, you can go out onto the GitHub organization and work with the Docker images. You might be interested in some of the analysis tools that we're developing and working with. And yeah, so I'd like to hear your requirements and get to talking with the community, and hear how people can contribute as well. So I hope that we're able to build the community together around Space ROS, and it does indeed create that revolution in space robotics. I think it will over time. It may take, like I said, several years to really build this up, and that's what I'm looking forward to. So I thank you for your attention, and hope you have a great rest of the conference. I have plenty of time to take questions, since I think I went a little fast, maybe a little nervous, but if anybody has any questions, I can take some of those. Thank you. Yeah.
Thank you for the talk. It's great to see the initiative. I've been watching it for some time. It's great to see some parts. My question is about micro ROS. What are the benefits of micro ROS?
Oh, micro ROS. Yeah, that's a great question. So, yeah, thanks for asking that. I'm very interested in that as well. And so there could be an architecture that perhaps, and we haven't gotten into this yet in Space ROS, but I have been thinking about this, because you could partition your system to have maybe a safety processor running micro ROS on an embedded system, and you could have a companion system. I think this is done in automotive as well, where there's maybe not such a stringent degree of requirements for that system. Right? So it's really an architectural discussion about how you partition your system. Our focus so far has been on the mainline ROS stuff, but I think that will probably be something that will come up in the future, because I think that's a very nice subset. Like I said, you can have very high, like maybe the monitor that I was talking about that's monitoring the system, or something that has super high integrity could run on a system. Sorry, I needed to repeat the question too, by the way. So he was asking about micro ROS. So micro ROS is a package that is intended, kind of compatible with ROS and can communicate with a full-blown ROS system, but is really kind of a stripped-down implementation from the company eProsima and Bosch. Oh, thank you. Yeah. So yeah. Yeah, you know, that another great question. Thank you. This is super. So I have thought about this as well. That there's other industries too, medical devices. So I think well, Apex is, as far as I know, it's closed source and not available. So it's not something we can directly work with ourselves. But I think in the future there may be something that could span multiple segments, right? And if we can, and I have been discussing this, is how do we, over time, support the certification in multiple verticals, right? We don't want to reproduce this work, you know, talking about reproduce for every vertical. So it's incumbent then that you have to understand, which is a large effort, these different standards. So, and I would imagine, but I don't know, we have to provide some similar artifacts. Can we have a core system that's providing artifacts that is supporting standards in multiple verticals is kind of the question. And so, again, that's something I think it will end up there. And, but we're starting with space because those are the relationships that we have at the moment.
For Apex, they've got 100 man-years.
Yeah.
This effort. Is time to market important for Space ROS? Do you have all the time in the world?
No, I know. It is a huge effort, and so I can't answer that question. It's a community, so it's been driven, like I said, initiated. NASA sees it as important. Blue Origin sees it as important. The others value it in the community. How will it be pulled off? That's where I'm saying, obviously, it's got to be a huge community-driven effort. It's not something that a little company like Open Robotics can do, because I'm aware of the time that it actually took and the effort that it took. So do they have time? I think they do have time, because this is like they're taking a very long-term approach. As I said, it's not like a company that has to be up and running. They realize that there's a long-term play here, but that means that people have to be engaged and interested and stick with it and fund it and continue. And again, we're not certifying Space ROS itself. We're trying to provide the artifacts and the support that, and make it easier for those projects. You know, if they see the benefit where if they use Space ROS, would it be faster than the alternative, right? And incorporating this. So that's a great question, but I can't completely answer, you know, how much time that they're willing to wait for something like that. Yeah, great. Yes?
Yeah, we will use space robots. And what about simulation? Like, we find it particularly challenging. Do you find like special gazebo, like space gazebo in the future?
A space gazebo?
Yeah.
The question was about, is there a space gazebo? I think that's an interesting question. I mean, gazebo is being used already for Viper. And so I think what a space gazebo has been or means really is, do you have the worlds? Do you have kind of the models of the rover? Do you have the, you know, there's a model of the lunar surface. And there's been a lot of work on the, I won't say the physics, but a lot of it on the lighting, things like that, to get the simulation more dialed in. So I don't think it's inherently a different version of gazebo per se, or a modification. The physics or the things. Yeah, no, those are, yeah. So, you know, dust in different environments and things like that. And yeah, I think you're right. I can't I'm not the expert on gazebo. I'm more kind of on the ROS side. But yeah, I think it's the right idea. I think it's kind of extending, refining gazebo to incorporate the issues that you would encounter in space. And they are encountering some, and those that I've heard about are more around lighting and the physics and getting it accurate in that environment. But yeah. Yes? If the environment was made open source. So I think the plan for Viper is that all of this software eventually will be open source. And so that will include the rover and the simulation environment and everything. I actually work on that project as well. So I'm part on the end-to-end testing. I'm helping with that, so I'm familiar with that. I don't know the exact timeline of the release of this, but it will be after the mission. They will release all of that as open source. Yeah.
Sorry, a bit of a softball question.
Sure. I can use one. Yeah, that was a hard one.
When I'm not busy with working on a satellite data company,
Oh, great.
And one of your slides you mentioned FIRST Robotics.
Yeah.
I've been a mentor for over 10 years. And like, what components of ROS are in FIRST Robotics? This is the first I've heard of it.
What components? Oh, I don't know. I've heard of teams using it, and I keep asking, because I was a FIRST Robotics mentor for a while too. My son went through high school, and I did that for a few years. And so my nephew has been involved. I'm like, are they using ROS yet? Are they using ROS yet? So I have heard of it, but I don't know specifically what. Do you know what the OS they're using now?
Well, it's all based on the National Instruments platform,
ROBO-RIO,
And
okay.
there is a library, a WPI that's produced by
Worcester. Yeah, Worcester. Yeah.
Which they interact with, like using Java or LabVIEW or C++.
See, when I was a mentor, I had them all doing C. So I was like, we were right on the system. I said, you guys are going to, we did source code control. We did, you guys are going to learn to do state machines. And they kind of abstract the kids away a little bit. I'd rather have them right on it. But that was a long time ago.
The solution is get them over to F110.
Okay. So, yeah. So I probably cheated a little bit. I've asked about that. I've heard that it's down there at the high school level, and I think it will be. I mean, it's so prevalent. But my nephew's going to OSU. I keep asking him, too. He doesn't even really know what ROS is. I go, you're going to find out what ROS is. You're going to come back to me and be like, you work on ROS? Yeah.
Yeah, I heard a lot of word testing, right? That you need to test, like end-to-end testing, like
Yeah.
the whole system, subsystem, and such. And my question would be, what are the challenges in different areas? Because you need to bring people, or you need to bring software, you need to implement solutions to test all of those systems. And what are the challenges related to that?
What are the challenges related to testing a ROS system?
Yeah.
Well, that's an interesting question. So I can think about it in terms of, there's different ways to look at that question. So I found with ROS, right, you're pulling a lot of packages together to create a system. And the testing is kind of oriented sometimes on a per package basis, right? Or maybe unit test or package. And when you put them together, you now have system behavior. So I think a challenge for me that I've thought about is that there's not really the system-based testing tools, right? Maybe there's some statistics you can pull off, but really it's characterizing the behavior of the entire system that you're putting together. It's really component-oriented. When you have a component-oriented architecture, I think the challenge becomes the emergent behavior of the system. So to me, that's a challenge. In terms of Viper on the end-to-end testing, I think part of the challenge, to be honest, part of the challenge was the testing tools. We kind of wrote some additional layers of testing stuff to do end-to-end testing to make it very easy, a kind of declarative kind of test that doesn't really exist yet in the ROS ecosystem. There's launch testing, and unit level tests. But again, the system level testing of what you want. In our case, it was kind of sequentially for the robot. Drive to a set point, take a panorama, or inject faults into the system so that the robot would think that the sensor was at a certain level. Does the robot behave properly, right? And so we're doing all those things to develop a testing framework for that robot, right? And so ultimately, some of the stuff we've done hopefully will be open source and it can be added. We've tried to feed some back. A lot of the things that we're working on a project like Viper, you try to feed back into the open source the things that are relevant and not Viper specific. But those are the challenges that I find. Does that kind of answer your question? What did you have in mind? What are you thinking of?
I'm really interested in all this in architecture and
Yeah.
testing stuff. So in our work, we find a bit challenging to create or to use some frameworks to do the testing.
Yeah.
And extract valuable information from the
Yeah, exactly. Yeah.
take actions on
Yeah, exactly. So part of what we did with Viper as well, so you want to do, speaking of extracting information, not only do you want to run through your test scenarios, but also sometimes generate the output data so you can do post-processing. For example, on Viper, what was done was to test so-called slip testing. So they're trying to match it to, like I said, these ramps. Do you have an accurate behavior in simulation? So you're going up and you can set the friction on the wheels and see how it's slipping and that type of thing. So there's a lot of scenarios run, lots and lots of tests, and we actually had some challenges kind of restarting Gazebo, for example, over and over and over and over and over, to run all these different parameters. And so there needs to be a system like that. System-oriented, driving the whole system, outputting data, running post-processing across all of that data to generate your charts and graphs and analyses and all of that stuff. So it was a pretty big effort to bring all of that up, but we have that now in Viper, and it's very useful. We can script a lot of these test cases. So what I wanted from it, so I kind of designed this on top of an existing layer, but have a kind of a YAML-based test description. Very easy. You just describe the operation and its arguments. The operation arguments go through, and a command abstraction or an asynchronous command, so you can plug in more and more commands, and you get kind of this network effect of now that you can use tested commands, right? People have already used these for lots of tests. The same thing that we're talking about here at the package level, but kind of at the test command level, right? And so this has worked out really well for us to have this internally. But yeah, testing can be a challenge for sure. All right, any more questions? I think that's it. We've got to clear the room for the next one. I think everybody has to go out and then they come back in for the next session. So again, thank you very much and have a great conference.